the end of the talk, we will have a free discussion with the audience.
Okay, that sounds good.
Okay. All right. So welcome you all for the virtual commutative algebra seminar. We are very happy to have Professor Jan Aberbach from University of Missouri in Columbia. He will speak on the equivalence of weak and strong F-regularity. So over to you, Jan.
All right, thank you. Yeah, I'll start. My goal is to kind of keep this more or less self-contained. I've seen, there have been talks on tight closure, but I don't think this topic has come up. And toward the end, I'll talk about some new results that Thomas Polstra and I got. And those, if you want to look them up, are in this paper, Local Cohomology Bounds and Test Ideals, which is on the archive. So let me just start with the kind of basic assumptions. My rings are Noetherian and commutative. They're, for the most part, going to be characteristic P prime, and I'll use D for the dimension. Actually, let me scrub this one for a moment. Oops. At a certain point, I'll assume they're kind of nice rings, but what we're saying early on is maybe a little more general. So I'm going to use Q to be a varying power of P. And then what is tight closure? Well, we start with an ideal I in the ring, and we take what are called the Qth powers. So that's the ideal generated by the Qth powers of elements in the ring. And this works very nicely. If I is generated by n elements, then the bracket Qth power is generated by the Qth powers of those same elements. This is the beauty of the Frobenius endomorphism. And I'm gonna do this whole talk without really ever thinking of the Frobenius endomorphism itself or the functor that comes from it. And then by R naught, I mean R minus the union of the minimal primes. And in particular, you really, for tight closure, you pretty much want to think about R is a domain, and then R naught is just R minus 0, so non-zero elements. If you just think about that context, you pretty much can deal with everything. So then what is the tight closure? Well, so Hochster and Hunicke began studying this in the late 80s. So we can define what's called the tight closure of I star of R. And what does it mean for X to be in there? Well, it means that there exists a C in R naught such that for all Q sufficiently large, C X to the Q is in the bracket Qth power. So this is kind of saying up to multiplying by a small order element, we're in higher and higher bracket powers. So sometimes we need to be clear about what the ring is, but if we kind of know what the ring is, we just drop the R and write I star. Okay, so an ideal I is tightly closed if, well, when you do this operation, you get back I. So I should point out that it's easy to see if we take X itself in I, then and C equals 1, every element of I is in I star. But this can throw some new elements in. All right, and it is a closure operation. I'll say more specifically in a few minutes. Quickly summarize the properties here. in order to explain the title, what does weakly F-regular mean? Well, R is weakly F-regular if every ideal is tightly closed. And that happens to be a particularly nice condition on the ring. And what does F-regular mean? Well, R is F-regular if for every prime P in spec R, the ring R localized at P is weakly F-regular. And the reason that you have to make a separate definition is that tight closure does not obviously commute with localization. And in fact, it doesn't commute with localization, which we'll talk more about a little later. And so you have to make up for that by making a separate definition. All right, so the goal of the talk is to essentially discuss, well, what can we say if we know this supposedly weaker condition? Can we get, does it imply that the F-regular condition holds, or as the title said, there's something called strongly F-regular, which I'll define in a little while. All right, so one thing about weakly F-regular rings, every ideal being tightly closed, in the case of principal ideals, the tight closure and the integral closure agree. And so that immediately implies that weakly F-regular rings are normal domains. And they're, I'm going to say for the moment, often Cohen-Macaulay under mild conditions. All right, so that leaves the open question I mentioned before. Does weakly F-regular imply F-regular? Okay, and so this is still open. So I kind of want to, a lot of the talk I just want to discuss, well, what does the equivalence involve proving, or what are ways to attack this? For those people who maybe haven't thought about such problems. All right, so let me mention a few of the basic tight closure that are useful to know. As I mentioned before, the ideal I is in I star, and the tight closure is in the, here, this is the usual notation for the integral closure. And it's called tight closure because, in fact, it's often much, much smaller than the integral closure. It's a much better fit to I. Then if we do the tight closure twice, we don't get anything new. So we get back I star, all right? And it's order preserving. So if one ideal is contained in another, then I1 star is contained in I2 star. Then another thing to note is that if R is a regular ring, then R is actually F-regular. I should say all of these things I'm noting were proved by Hochster and Hunicke in their original papers. So in a regular ring, every ideal is tightly closed. but that doesn't characterize regular rings, or having all ideals tightly closed does not characterize regular rings. Many other rings have that property. Okay, so here is, say, one situation where we can answer the question that we asked earlier. If we have A contained in R, such that A splits out of R as an A module, then if the ring R is weakly F-regular, ring A. So that implies that A is weakly F-regular. Some ends of regular rings all have this nice property. And then lastly, if we get to the kind of the crucial computation, if we take a multiplicative set, W, then we can look at the following. We can compute I'll be really pedantic, right? The localization of I in the localization of R, and we can take the tight closure. And we can also compute the tight closure in R and take the localization. And it is true that there is a containment this way. This is fairly easy, but what is the real question is, does the opposite containment hold? Right, and unfortunately, it doesn't. So another way to say that is in this form. If we compute that tight closure in the localization and contract back to R, do we get the tight closure in I? Let me think about what this says. Suppose say we have X over W in the tight closure of the extension. Okay, well, we can choose a C over 1 this would be in W inverse R naught, where C is in R naught. So that's not really an issue. The element that we use to check tight closure is we can always kind of get back into R. So what does this say? It says such that that C over 1 X over W to the Q is in, well, so that's in I W inverse R to the Q. And so if you write everything down and unwind this, i.e. for all Q, well, sufficiently large, this is for all Q sufficiently large. For all Q sufficiently large, there exists a W sub Q in W such that WQ C X to the Q is in I to the Q. All right, so essentially we're clearing denominators of the fractions, but right, so then so if we have say a W1 in W such that WQ is equal to, say, W1 to the Q, then we'd have C W1X to the Q is in I to the Q. I.e., that would say W1X is in I star in R, and that is what we would want to happen, okay? So I'm just going to say as desired, right, to get into W inverse of I star R. All right, but this in fact is really hard to control. So this is neither obvious, nor is it true. So that's the problem. In the for the general case, and I believe, yeah, I think it was here I wanted to say. So in fact, Brenner and Monsky gave a counterexample in 2010, or the paper appeared in 2010. So there exists a K algebra R and an ideal, an ideal I contained in R and a P in spec R such that let's see, so which the IRP star RP contains properly I star R localized at P. So this just doesn't work. And their example, the proof for their example is, well, I admit I can't understand it completely. The example itself, though, is not some crazy ring that's, you would never look at in a million years. It's not that complicated a ring. Okay. All right. So so what I want to do now is concentrate on the weaker question. So maybe I should write that down here. So the thing is, this example does not show or does not, let me give a counterexample to weak implies strong. That's my shorthand for weak F regularity implying strong F regularity. And I guess I should mention it's still kind of open. I don't think, actually Modi is probably one of the people who might be able to correct me here if I'm wrong. I don't think there's a local example where we can, with a local ring where we can localize, or that we know we localize and things go wrong. But I'm not 100% sure about that. Okay, So for the rest of the talk, now I want to actually assume that we're in the local case and that the ring is reasonably nice. And so the excellent is a strong condition. For those of you, if you don't know what excellent is, just think about complete rings. Okay, so these are just behaved much better. So one thing I wanted to mention is, so in the non-excellent case, you can get kind of catastrophes right from the start. So for instance, you might, one of the first questions you want to ask is if a local ring has a property, does its completion have the property? So if a local ring is weakly F-regular, is its completion weakly F-regular? And unfortunately, if you kind of apply the Heitman school of thinking, that basically you can always form UFDs that give you any completion you want. There are examples of local rings, Gorenstein local rings that are F-regular, weakly F-regular, and the completion is not. But those are non-excellent rings. That's actually a result of Susan Lepp and Crystal Ruthouse. So we do need some condition on the ring, the local ring, to get anywhere in this question. Okay, so under that hypothesis, it turns out that there are some really nice properties of this multiplier C. So in the definition of tight closure, there is some C. For each element X, there is some C that works if X is in the tight closure of I. And but it turns out that in nice rings, there are elements that always work. So I'm going to make that definition. Again, this is a definition coming from Hochster and Hunicke. We'll call C in R naught a test element for R if, well, what does that mean? If for all I contained in R, if X is in R star, then C X to the Q is in I to the Q for all Q. Okay, so not only does it work for all test, does it work to show something is in the tight closure, I even want it to work for all Q. And when R is a domain, that's if you can find something that works for all Q large enough, you can find something that works for all Q.
Yeah, Ian, you mean I star, not R star.
Oh, yes, I certainly do. Let's correct that. Thank you. Right. It wouldn't be much of a definition if it just had to do with R star, would it? Okay, so Hochster and Hunicke, H and H is Hochster and Hunicke, nothing to do with bagels, showed that when the ring is, a local ring is excellent and reduced, then there's a big source of test elements. So if you take an element C such that the localization is regular, then in fact, some power of C is a test element. Okay. All right. So then let's call what I want to define test ideal. All right. This is what's known as the big or completely stable test ideal. So we use B for that. This is the ideal generated by test elements. All right, and so Hochster and Hunicke's result says that this is a non-trivial ideal. But I want to look at, I want to get at this ideal, the test ideal, in a different way. So I want to look at the injective hull of the residue field, okay? And so let me start by pointing out that in the nice situations, we can actually write E as a direct limit. Okay, so Hochster proved the following. If we have a local ring that's excellent and reduced, and this is not characteristic dependent, so this is for any excellent and reduced ring, then what we can say is there exists a descending sequence IT of M primary irreducible ideals such that and maps such that the direct limit of the R mod ITs is a copy of the injective hull. Okay, these are all irreducible. So there's if you take one and contain in another, and you look at the quotients, you can map Sockle element to Sockle element. So there's kind of a natural way to fit these all together, and that direct limit is E. And so what I want to do next then is to think about within this module E, 0 is a submodule. What is its tight closure? Okay, so what is the tight closure of 0 in E? Now, I've only defined tight closure for ideals, and there is a more general definition of tight closure for one submodule of another module using the Frobenius endomorphism. But I want to completely avoid that today. And so this allows us to do that. So let's look inside E. Let's take an element eta. And I want to know what does it mean that eta is in the tight closure? Right. Well, so we can write eta as basically it's a coherent sequence in the direct limit. Right, so eventually, so for starting from some t large enough, we can view this eta as being a class. Right? And so it says, so then we have that multiplier C in R naught. Well, so C eta to the Q should equal 0 for Q sufficiently large, right? And of course, this, we can take our test element. But what does that mean? That means that for all Q, if you wish, sufficiently large, that in terms of the x's, it's a direct limit. So yeah, I shouldn't say coherent sequence, a sequence that represents eta. I confused you with that. So that says for all Q greater than big enough, essentially what you can see, you can get from this is that there exists a T, I'll label it right, depending on Q, such that C X sub TQ to the Q is in I sub TQ to the Q. All right, that's what it means essentially for, right, I didn't really say what eta to the Q means, but I mean this. And so the problem is that T sub Q depends on Q, right? Right, T depends on Q. And that's where the problem is often, okay? All right, so for that very reason, Hoxer and Hunicke defined what's called finitistic tight closure. And so they threw in this FG for finitely generated. And so let's say that we're in the finitistic tight closure. So let's take that this element eta and say it's in the finitistic tight closure if basically we can bound that T. So if there exists C in R naught, and there exists, say, some T naught greater than or equal to 1, such that for all Q here, we can even be sufficiently large, C X T naught to the Q is in I T naught to the Q, right? And i.e. that says X to the T naught is in I to the T naught star. All right. So one way to view this from this comment is that this finitistic tight closure you can think of as the direct limit of the tight closures of the IT. Okay, and the second condition, if we look at those two conditions, right, this is a more restrictive condition than this. And so the finitistic tight closure is going to be in the tight closure. All right.
Ian, there's a question from Miyazaki. He says, what are the maps in the direct limit?
Let me come back up to where I define that. I mean, part of the theorem is that there are such maps, but essentially what you've got is, let's see. So you've got R mod, you've got R mod IT, you've got R mod IT plus 1. And remember, these are irreducible, okay? And so there's a Sockle element UT in here. There's a Sockle element UT plus 1 in here. And so this is if we look at that, these are both copies of K. So that's an isomorphism. And then these are injectives, so it lifts. So we can kind of do that at each stage. Does that help?
Yeah, yeah.
Okay. Yeah.
Okay.
All right, so let me now, I want to relate these two tight closures and then the test ideal that I introduced earlier. So here are some definitions and theorems that are connecting the tight closures in E, the various F-regularities, and the test ideals. All right, so again, let's assume our ring is excellent and reduced. Okay, so then the big test ideal, tau sub b, we can view in it, it is in fact the annihilator in R of the tight closure of E, the tight closure of 0 in E. Okay, and I'm not saying that that should be obvious. All right. So let me find the test ideal. I guess I should have labeled this. This is no big, so this is the test ideal. Tau b to be the annihilator of the finitistic tight closure. So the annihilator in R of 0 star Fg of E. All right, well, R is weakly F-regular. Well, being weakly F-regular says every ideal is tightly closed, which means you can test tight closure using 1. And this happens to be the same thing as saying this is if and only if this tau of R is equal to R. And so notice that, right, it's this module is smaller than this module, right? So we could have this being R, but this might not be R. This might be a proper ideal. And so I'm going to call R strongly F-regular. Let me make that definition. If the annihilator of in R of 0 star E is equal to R, i.e. if 0 star E is equal to 0. Nothing gets into the tight closure of 0 in the injective hull. Now, this actually makes sense in any excellent ring. When the ring is what's called F-finite, meaning that the Frobenius makes R into a module finite extension of itself, this can be connected to having a lot of splittings of R outside from the pth roots. Okay, and if I have time towards the end, I'll talk more about that. So really now the question we want to ask is tau of R the same thing as the tau big? So I've kind of summarized some of these questions. Well, actually, this is a theorem. Let me mention this. The strongly F-regular rings are F-regular. So it turns out this is a condition that one can localize. And at this point, I want to mention, because we have the excellent assumption, if we're weakly F-regular, then R is normal, and it is Cohen-Macaulay. So these weakly F-regular rings are really quite nice rings, right? And as we've seen above, the test ideal contains the big test ideal. And so we're really asking the question, are they equal? And then one can also ask the question, do they localize well? And the here's the thing. The big test ideal, which is smaller than the test ideal, unfortunately, is, or could be, this ideal is very well behaved. But this ideal, without knowing that they're equal, is not at all clearly well behaved. All right. So I should point out that Gennady Lubeznik and Karen Smith proved that this ring localizes well, i.e., if we look at tau big R extended to R localized at P, this is the big test ideal of R localized at P. And then I forget all the distinctions. I think what Lubeznik and Smith did was like maybe the complete case, and then myself and Florian Enescu extended that maybe to the more general excellent case. But the ideas were essentially the same. So it's this ideal, this big test ideal, or correspondingly the tight closure of 0 in the injective hull, which localizes well. The tight closure in the injective hull itself can't localize well because that's supported only at M, but you can kind of ask, well, you know, what happens when you localize? How does the tight closure compare via duality within the injective hull of the localization? And essentially those are all nicely behaved. Okay, so finally we I'm almost out of time, but we get to the question I asked at the beginning. So does weak F-regularity imply strong F-regularity? So that's saying if I know the finitistic tight closure is 0, do I know the tight closure itself is 0? And we can also phrase that in terms of the test ideals. All right, so I should spend a few minutes telling you what's known and when. For instance, very early on, Hochster and Hunicke showed this is true if R is, say, Gorenstein. Okay. Laurie Williams proved in her dissertation that yes, if the dimension of R is at most 3. Brian McCrimmon in his dissertation proved yes, if R is Q Gorenstein on the punctured spectrum, all right, by Q Gorenstein, what I mean is that these are Cohen-Macaulay rings. They have canonical modules, at least in the complete case, and those, because this is a domain, we have canonical ideals, and that's a torsion element. Being Q Gorenstein means that's a torsion element in the class group. So as long as you're away from the maximal ideal. Lubeznik and Smith did this for graded algebras over a field. And then Anurag Singh which was never published, Anurag Singh said, so this would be yes, for rings rings with Noetherian anti-canonical cover, and let me explain that in a little while when I get to some of the newer results. Okay, so I want to go back to these expressions for the for E, okay, and what it means to try to understand the tight closure or the finitistic tight closure. All right, so now I want to assume that R is Cohen-Macaulay and a normal domain. Right, so in that case, there's a nice source of these ITs. Okay, so then R has a canonical, maybe actually, and let's say has canonical module. So again, in the complete case, that's automatic. Then R has a canonical ideal, J, I'm going to call it J, contained in R, and J, this is a height 1 unmixed ideal. All right, so, and it's also, we can, the normal condition that says we can write, we can choose an element A in J generating at minimal primes of J. All right, and I'm going to write, let's write the ideal AR. This will be J intersect something called I, and this is an anti-canonical ideal. That's what I'm going to mean by the end. It's the inverse in the divisor class group, or the negative of J. So I didn't make this very clear. I want to say what these ITs are in this case, or one choice of the ITs. So what we can do is, so we can pick let's see, so x1 in J and x2 through xd in M, such that, I guess, the sequence x1 through xd is a system of parameters for R, and 2, x2 through xd is a system of parameters for R mod J. R mod J is dimension d-1, and in fact, it's Gornstein. Okay, and then we can take IT to be x1 to the t-1j, x2 to the t, xd to the t. And if U, say U naught, is the Sockle mod J x2 through xd, then if we just multiply by x1 through xd to the t minus 1 u, this is the Sockle mod IT. So this is a very understandable way to get at the injective hull. And so what this comes down to, so the question determining, let me write it this way, I guess, determining if 0 star E equals 0 star the finitistic tight closure in E, it comes down to the following, and I'm gonna maybe skip over a step or two since I wanna I don't want to go too far over. If we know that C, I'm just U naught. So here I'm going to have X. The X1 you can kind of get rid of. So it becomes X2 to the T, XD to the T. I'll put minus ones. U naught to the Q is in J X2 to the T X D to the T to the bracket Q for all Q sufficiently large. Then is it true that for some D in R naught, we have the freedom to multiply by something in R naught, that there exists a T naught. Oh, so I'm sorry, I didn't quite quantify this right. So if we know that there, I said this wrong. If we know that for all Q sufficiently large, there exists a T. So let me take that away from there. All right, so the quantification is the important part, so I shouldn't have gotten that wrong. So for each Q, there is a T. Do we know, can we switch the order? That there exists a T naught such that for all Q, say sufficiently large, D, C, this time X2 through XD, I guess I can write it this way, T naught minus 1, U naught to the Q is in J X2 to the T naught, XD to the T naught to the Q. So that's the question. It all comes down to switching the order on this of the quantifications. And essentially, in the list of in the history, the key result here is that knowing that your Q-Gorenstein on the punctured spectrum allows you to get these bounds. And that was what Laurie did in dimension 3 as well. These have a different method. And so that's where all the difficulty is. And it seems really straightforward, but it just doesn't doesn't work out very nicely. Even if this guy is 2 generated, it seems almost impossible, and it's mixed up with having infinitely many associated primes to these Qth bracket powers and various other things that come up. So let me finally get to some new results. Here's what Thomas and I were able to prove. So again, we have an excellent Cohen-Macaulay normal domain. And we have this canonical ideal J, and then the anti-canonical ideal I. So if we assume that the ring is Q-Gorenstein at height 2 ideals, and in the case that R is weakly F-regular, then there's a result of Lippmann, a hard result of Lippmann that guarantees that, because these are F-rational surfaces in dimension 2. And then what we realized is that previously we'd been focusing on this ideal J. What happens when we take, can we make this thing be principal if we take symbolic powers? And so when we can, that's McCrimmon's theorem, but in general, it isn't. Okay, it's not likely to be a nice ideal. We realized we could look more closely at the anti-canonical ideal. So suppose that there exists a symbolic power of the anti-canonical ideal such that we can put a condition on this ideal K. So for all P in spec naught of R, the analytic spread of K localized at P is at most 2. If you want to deal with J, you've got to get the analytic spread down to 1. And that just doesn't happen. But if you deal with the anti-canonical ideal, you only need the analytic spread to go down to 2. And in that case, what we can do is then we can show that the finitistic, the tight closure in E is the finitistic tight closure in E. So in particular, if R is weakly F-regular, then R is strongly F-regular. And like I said, the paper is on the archive. It's quite a long proof. It's not at all direct, so I didn't want to try to present the proof in the talk today. But I do want to finish up by mentioning, I left a little room to talk about the proof, but I think because it's already it's already the end of the hour, I won't. But I did want to mention one other thing, that there's been recent progress in the minimal model program that allowed us to actually say something kind of nice. So Das and Waldron proved something I don't understand very well, but if we have a local ring, which is a KLT singularity, essentially a finite type over a field, as long as the characteristic is greater than 5, and if the dimension of the ring is 3, and that I is our anti-canonical module, then the symbolic power algebra is Noetherian. Okay, so that had been conjectured and they were able to prove that. In that case, the Noetherianness of this guy and the dimension being 3 says that some power of the anti-canonical module has analytic spread 2 or less, which is our condition that we want. And so as a corollary of our results and theirs, if we take this F-regular ring, so we can't assume weakly F-regular. If we take a dimension 4 ring that is F-regular and has the right conditions to apply the above theorem, then the F-regular assumption, remember, is that every localization is weakly F-regular. So in dimension 3, we get to apply this result, which means the hypotheses for the earlier theorem are satisfied. And so then we can conclude that that R is strongly F-regular. Okay, and I guess I will stop there. I was hoping maybe I'd have time to say something about Hilbert-Kunz multiplicities. I noticed that there was a talk by was it Watanabe, maybe talking about these minimal the relative Hilbert-Kunz multiplicity, and there are actually some applications here for showing that if you do know what signatures are and relative Hilbert-Kunz multiplicities, we can show under the same hypotheses that the signature is actually achieved as a relative Hilbert-Kunz multiplicity. But I think I'll stop there. So
thank you, Jan. Thank you very much. We now take questions. Are there any questions? You can open your microphone and ask questions. I have a question about rings of invariants, whether if they are Cohen-Macaulay, are they strongly F-regular?
Those are mostly, yeah, I think in that situation, they're generally, aren't they, you know, as long as they're summands of regular rings. Well, I guess, so is that, I think most of the examples of rings of invariance that are nice, that they are known to be strongly F-regular through maybe through separate different methods. Right,
but if they are not Cohen-Macaulay, then
they can't. I mean, if they're not Cohen-Macaulay, there's no chance, because a weakly F-regular ring that's got any nice, you know, that's nice at all is going to be Cohen-Macaulay. So nothing non-Cohen-Macaulay can be.
Yeah.
I'm afraid I don't know much about rings of invariance kind of as a general field. So
yeah. So in this corollary, the dimension of R is 4. That is because in the Das theorem about Das and from Das,
yeah,
that they are saying dimension of R is 3.
Yeah, exactly. So in other words, what's happening here is, yeah, we want to apply this theorem. This theorem, the question is, what happens on the punctured spectrum, right? Mm-hmm. And so we don't care if we take a 4-dimensional ring. We don't care what happens at M, but we care about all the lower dimensional primes. And so the height 1 and 2 are captured by, you know, at height 1, you're regular. At height 2, you're an F-rational surface. So Lippmann's result applies to give you everything you need. It's what happens at height 3 primes, and then that's where the Das-Waldron result is so key. And even again, I don't want to. I'm not at all really. I don't know that much about the minimal model program. I believe you know, it's possible that the dimension 3 condition isn't necessary here, right? That, I mean, I think there's a belief that it may be true in higher dimensions. The Das-Waldron result is true in higher dimensions. But even if that could be proved, that actually would not help us get dimension 5, because then you'd be asking about, you know, what happens in this case when you're dimension 4. All you would know is that the analytic spread is at most 3. And this is kind of one of those situations where as soon as you have a 3 generated ideal, everything can go wrong. Whereas when you have a 2 generated ideal, you can kind of handle it in a way that allows you to get what you need.
Yeah. Okay. Any other questions for Ian?
There is one question in the chat box.
Okay.
Does the last corollary hold when R is weakly F regular?
Okay, so the problem, if you assume R is weakly F regular, then what we don't know is that at a height 3 prime, that the ring is weakly F regular at the height 3 prime, right? Because the condition weakly F regular isn't known to localize. And in that case, I think we don't get this condition holding. And so it's not enough to know that. We'd need a better way, right? We have to know it we have to know the nice conditions in codimension 3 at height 3. So yeah, it can't be applied.
Okay.
Thank you.
Any other questions? Okay, if not, let us thank Ian for his very nice talk. Yeah, you can clap. And we would like to have your slides to be put up on the website.
Okay, yeah, I can email those to you.
Right. And okay, thanks again for coming over, and let's hope we will meet again sometime physically.
I hope soon. I want to thank you guys for inviting me. I really appreciate it, and it's nice to be able to be here. I guess I should have thanked you at the beginning of the talk, but it's great that you guys are having this wonderful seminar. So.
Thank you, Ian.